Good morning, friends. What I'm going to do on this, I think, short video is continue a little bit sharing some Python, the generator construct, but also elaborating on the Jitterbug, or really the concentric hierarchy, which is just a stacking of polyhedrons, a maze, a labyrinth. It's a sculpture, and you could think of this as art school, and you need to learn a little Python. And so we take a very abstract, arty kind of topic that's very geometric, right? So I'm going to talk about some of the concepts. Let me set up the terminology and then come back and complete the demo. So this icosahedron inside of an octahedron. This is something, you go back, you'll find it in ancient texts. It's not a new discovery. What we're looking at, let's see if I can find the clearest picture. Well, it's a double picture. First of all, we have a cube octahedron, and this is going to be the 2.5 in my particular demo. So what I'm going to do is say, how do I go from this cube octahedron to another shape, an icosahedron, but with the faces all still pushed up against each other? In other words, the icosahedron's face and the cube octahedron's face, they're just tilted, but they're in the same plane, but relative to one another they've tilted. And what have they tilted inside of? A common face, the common face of an octahedron. So this is an octahedron with an embedded cube octahedron, which is easy to understand, and then a skewed icosahedron. Okay, keep those two concepts in mind, icosahedron and smaller cube octahedron. Let's go over to here. We want to have a bigger icosahedron inside the volume 4 cube octahedron. So on line 13, where I'm at right now, I'm going to put a stub here. I'm going to say, let's see, what should we call it? Icosa within, which reminds me, it inscribes inside of the what? It inscribes inside the octahedron of volume 4. So what I hope to do here is show you that going from the 2.5 times the S factor times the S factor, two applications of the S factor, is going to bump the 2.5, that's going to bump that 2.5 up to the icosahedron that it needs to be. So this is not a jitterbug. And yet coming the other direction, I want to show you that 20 times the inverse of the S factor is going to be taking us from the cube octahedron to the icosahedron in the jitterbug transformation. So these are not the same transformation. One of them is it's making something bigger. It's taking a cube octahedron and turning it into an icosa that's bigger. Going in the other direction, we're shrinking down. We're taking a cube octa down one level to an icosahedron that has the same edge lengths. Now this is different coming up, getting bigger. It's not the same edge lengths. So what I need to define now to make this work, and notice it's not yet symmetric after we go through 0. Let's fix that. I know this is maddening now to do this kind of tedious stuff but you could think of it as a kind of a hand-eye coordination or something, like where does this fit in? I'm actually thinking of something getting bigger here, a cube octahedron. I recommend going back to my previous video, Jitterbug number 1, if you want to get some more background on this jitterbug. So this is kind of what I'm trying to say. And let's see now if it works. And the question is, what's the S factor? So the S factor is going to be the volume of the S module ratioed to the volume of the E module. And now you're going to ask, well, what the heck's the S module and what the heck's the E module? So I need to just solve these two. And I'm going to do it two ways. First of all, I'm going to jump over to REPL.it, and scroll down through some old Python here and just pull up some values in S and E modules. So I've got them stashed here. You'd think I'd have them memorized, wouldn't you? But that's more David Koski's on top of that. He's on top of that. You see I quote his paper here, and these are what we call Koski Identities. So what I'm going to do is get the golden ratio, which means I need the second root of 2 in my code. So we just copied it over. And now we're going to get the S mod very simply as an expression of the golden ratio. And the E module's got to be here somewhere. There it is. Never mind exactly about the... Okay, so those are capitalized. So what I will do then instead is accept reality and say the S factor is capital S mod over capital E mod, and I think we're done. All right, let's first again show what is the E mod and what is the S mod visually, and then we'll run it. So visually, this is the S module is the difference between that icosahedron inside and the icosahedron. Okay, let me find a better picture here. That's the volume 4 octahedron I've been talking about, and that's icosa within. And this is the S module. 24 of them build the difference between those two. So if you want to brick in an icosahedron, faces flush with an octahedron, to create that full octahedron, you must add 24 S modules. I mean, that's one way to do it. And 24 means 12 left and 12 right-handed. Now the E module, we've seen many times. It's been our friend many times before. You can see it here as 1/120th of a rhombic triicotahedron. So we have a 30 diamond-faced thing. There's only one of them here shown twice. And what we're doing, let's get the rhombic triicotahedron up next to the rhombic dodecahedron. There it is again. It only has 30 diamond faces, but we crisscross and cut them into 4, each of those diamonds. So 4 times 30 is 120. An E module is one chunk of that, one pizza slice, left to right. So going back to my code here, there you go. That's the volumes in tetravolumes. So we have a unit volume, remember, that's on line 22 and 24. Now we're ready to see if any of this makes sense, or did I make a mistake? Could have. Could have. So let's do a for loop. No, let's not. Let's create, we'll call it concentric hierarchy equals Jitterbug. I didn't get any crashes, so that's a good sign. And now I'm going to go next. You know, I could start at 24 too. That would be a 2-frequency cube. I could have 24 bracketing this thing, but let's not do that today. 20, okay, now we want to go down to the 18.51. And I want to get there just by multiplying by the S factor to the -1, i.e. 1 over the S factor. There it is. Now we want to keep going down. So next again, hit the octahedron of 4. Now I want the icosa that's faces flush with this 4 to have some kind of volume that makes sense. I'm not going to be able to prove to you probably that it is correct here, but it should of course be bigger than 2.5. It's 2.9179, blah blah. Okay, going down further, elevator down. Now we've hit the cube octahedron of 2.5, and now we're hitting the tetrahedron and we're on the ground floor. There's a go through 0 to the basement, but it's not really a basement. We start going up in some other reality. That's just the science fiction. You can map whatever you want onto it. It's art school after all, but I just wanted you to learn some Python here. And out to 20, could go to 24, and then bow tie and go back. All right, I hope you learned something in that, and we'll start again next time.